So another type of model that's good for periodicity, but is much simpler, is called a seasonal means model. And so this one, we would just use the means for each time period. So for example, if we were thinking about the monthly butter imports, Danish butter imports, we could have a model with a beta 0 plus beta 1 for the month of February, beta 2 for the month of March, up through beta 11 through the month of December. And of course, one of the months is going to get used as the reference group, get baked into the intercept. And so we're not going to have 12 comparative coefficients. We're going to have 12 coefficients overall, including beta 0, which is our intercept. So let's think about how this would work for my Danish butter imports. I'm going to use the month as a factor. And now I've got all of these comparative values in my regression output. So compared to January, we would expect the mean in February to be 3.8 lower. Compared to January, we'd expect the mean in March to be 8.17 higher. Compared to January, we'd expect April to be 25 higher, etc. And so we could write out 12 different regression equations. So we could have our y hat for January, which would just be 169.8. We could have our y hat for February. That would be 169.8 minus 3.8, which would be 166. We could have our y hat for March, which would be 169.8 plus 8, which is 177.8, etc. So let's think about how that model would look. So again, I'm using blue for my model, and what I've done here is I've just connected the dots between the predictions. So I'm going to use green here to just mark off the means. So the data actually starts in February. So this would be the 166. And then we would have the data for March, which I think is here at the 177.8. Let's go one further and try and figure out what the value would be in April. So that would be 169.8 plus 25.7, 195.5. Oh, so I think this one was actually the 195, and probably there's a point that we can't really see in here that's at the 177.8. Let's see, what's the highest point here? Must be the one with the biggest difference, so that's June, which is 85 higher. So this would be June, and June, and June. And so we've got the same prediction for every June all the way across. We've got the same prediction for every February all the way across, and etc. So we're just taking those means and we're connecting the dots. So there's only 12 points per year, just like there are with the time series, but we're connecting the lines between them. Again, I think that this model looks pretty good, and it's certainly capturing that periodicity, even though it's pretty simple. So if we're going to compare between the cosine trend model and the seasonal means model, one thing that's good about the cosine trends model is that it has very few parameters. It just has 3 parameters, versus the seasonal means model, which has lots of parameters. The cosine trend, if we look at the R squared, it's not as good as the one for the seasonal means. Seasonal means has both better R squared and adjusted R squared. I don't think that I found the adjusted. I think this is just regular r squared here, but the adjusted r squared would be even lower. So this one is doing better with the r squareds. It has lots of parameters, which is kind of a drawback, but it's also a benefit because those coefficients, the parameters are interpretable. I can give you a sentence saying that, compared to January, May, we would expect 54, whatever, more imports of butter, versus I don't have a sentence for this negative 33.7. I don't know how to interpret that. Let's do another example with some periodicity. So this is also from the butter data, but instead of the number of imports or the volume of imports, this is the price of butter. So this still has some periodicity to it, but there's a little bit more going on. So if I fit that seasonal means model, I get those same kind of coefficients, and I could do a model that would look like this. And we can see that it's capturing the periodicity, but there's something a little bit more going on. So when we look at the residuals of this model, we've got very positive residuals at first and then negative residuals afterward. So there's clearly still some trend that isn't being explained by those seasonal means. And so we could include another term. We could include a linear trend where we just put month in as a numeric variable. And so for, as months go on, we think that overall things are going to go down while holding everything else constant, while holding, the sort of month factor constant. And so if we look at that model, that looks a lot better to me visually. So we've got the up and down over time, but we also have an overall negative trend. And the residuals, I think, are looking better. They don't have that linear trend. There's still some curvature, so there still might be some variability that we could explain. We could probably do better in modeling this data. So when we think about time series, it's often useful to think about time series as a decomposition. So this is my original data set of the butter prices. And I could think of decomposing that into a linear trend, which is negative, a seasonal means trend, which has some periodicity, and then the residuals, the variability that's unexplained. So we could think about this piece being equal to this piece plus this piece plus this piece. So it could be broken down into those three pieces. So that was kind of 12.1, where we were just thinking about linear regression and how we could modify it to talk about time series.